Okay, for the third of our series looking at chemical bonding, we will look at ionic bonding. So, ionic bonding happens between metal and non-metal atoms. So I've picked an example here using sodium and chlorine. And once again, the key thing is things having full or empty outer shell. So we've got sodium here, element number 11, 281. Chlorine number 17, 287. Sodium would like to lose one electron here to get to an empty outer shell. Chlorine would like one more electron to get to a full outer shell. So this is what, if you like, drives this bonding process again. And what happens in this case here is that the sodium gives this electron here over to the chlorine. So when that happens there, the sodium in a sense has lost one electron, so that becomes 280 now, and it's got 10 electrons and 11 protons, so it becomes a sodium ion with a positive charge because it's got one less electron. The chlorine has now gained an extra electron once that one transfers over, so that has 288, has a negative charge because it's got the extra electron. So now we have two oppositely charged particles and opposites, or in this case opposite charges. Opposite charges will attract, and that is what will form the basis of that ionic bond, the basis of the force, if you like, that holds those two atoms together. However, it's not quite as simple as that. What actually happens is we don't just get one sodium and one chlorine atom bonding together. We get the formation of this continuous lattice of sodium and chloride ions, which are all held together by that electrostatic force due to the opposite charges in a network. So if I was to draw that out, what that more looks like, if we could look, at least this is a two-dimensional representation of what we would see if we could look inside sodium chloride, which you probably know is just general normal table salt, is you would see this continuous lattice of the positively charged sodium ions and the negatively charged chloride ions, something like that. So that would be the structure. So we call this sometimes, when we put the formula for sodium chloride, which is NaCl, we sometimes call this an empirical formula or a formula unit, because it's telling us the ratio of sodium ions to chloride ions in this lattice. So if we say we've got sodium chloride, we don't just have one sodium atom bonded to one chlorine atom. We have a lattice with a 1-to-1 ratio of these two atoms. The other thing that's here, which I've already covered earlier, is it talks about, obviously, all this is about the formation of ions, which I covered in an earlier video. I think I said at that time I'd sort of jumped ahead. So most of this stuff here that talks about writing the electron configuration for the ions, we've already covered in an earlier video. And once again, that was all related to getting full or empty outer shells. That's what drives that whole process, and therefore drives the ionic bonding process. So now, just exploring ionic bonding in a little bit more detail. Firstly, the naming of compounds. When we name an ionic compound, we always name the metal first, and the ending of the non-metal is changed to "ide". So what does that look like? If we've got sodium and fluorine combining to form an ionic compound, we would call that sodium fluoride. So we change the "ene" on the end to an "ide". Calcium and oxygen would become calcium, metal first, oxide. So change the ending of the non-metal to ide. So we do that for all of the ionic compounds, always metal first, then non-metal, and always change the ending of the name to ide. We do need to do something slightly different when we do with polyatomic ions. I did cover that, I know, a lot in year 10, but if you need to talk to me about polyatomic ions, I might even make a short video about polyatomic ions as well. The other thing we need to do is balance out the formula. We don't always end up with one metal ion for one non-metal ion, like we did in the case of sodium chloride in the previous slide. What we need to achieve is a balance of positive and negative charge. So lithium is in group 1, so it would have a positive charge. Chlorine is in group 7, so it wants 1 electron, a negative charge. The positive and the negative cancel out, so that would be lithium chloride. It would be a 1-to-1 ratio. However, if we had calcium, which is in group 2, so it forms a 2+, and then sulfur, which is in group 6, so it wants 2 electron, forms a 2-. Now we've got a 2+ and a 2-, so this one does cancel out again. So we could just have 1 calcium to 1 sulfur because the 2+ cancels out the 2-. When we get to potassium, group 1, so that has a 1+, but oxygen is in group 6, so it wants 2 electrons, so it has a 2-. So the 1+ doesn't cancel out the 2-. If one positive thing happens to you and 2 negative things, you're still going to feel a bit negative. What do you need? You need another positive thing. So we would need to put a 2 down there. So we would need 2 positive potassium ions for every 1 oxygen ion that has a 2 negative charge to balance out the charge there. Gets a little bit more confusing with this next one. Aluminium has a 3+ charge because it's in group 3. Oxygen has a 2-. How do we make those balance out? If we have 2 oxygen, then we have a 4-. So then we've got too much minus charge. So what can we do? What we need to do is find the lowest common multiple. If we think about it in mass, the lowest common multiple of 3 and 2 is 6. So if we have 2 aluminium, that would give us 6+. 2 3s are 6+. And if we have 3 oxygen, that would give us 6-. So that would then balance out. Now, as I've done these, I've written the charge on as I've done them. And when you're starting out, that's fine, and I won't take marks off for you for this year. But strictly speaking, good practice is we don't actually leave the charges when we write the formulas out. So you really should write out the formula for, say, aluminium oxide like that without those charges. So as you get good at them and you don't need to do that working out, don't worry about putting those charges in. If you're putting them in at the start to work it out, that's perfectly okay. Now, let's just talk finally about the properties of ionic compounds and how it relates, or how it is explained by the bonding model. So they tend to have very high melting points, and that's because of the strong electrostatic attraction between the positively charged metal ions and the negatively charged metal ions. We saw that in the previous slide in that diagram of the lattice. So it's a bit like the metals, that lattice of positive and negative charges holds everything together really strongly. They can't conduct electricity in their solid form, and that's as the ions are not free to move. So those, say in the sodium chloride example, the sodium ions and the chloride ions can't move in the solid form. So they tend to be, so they won't conduct electricity in the solid form. However, if you melt them, so they become molten, or you dissolve them in water, those ions then become free to move. So molten salts, or melted ionic compounds, salt is another word for an ionic compound, so melted ionic compounds or dissolved ionic compounds, where the ions have become free, will conduct electricity as the ions are free to move in those forms. And finally, I'll talk about why they are brittle. But just before I do that, I'm just going to pause to do a little diagram to explain that. So, we've got our sodium chloride lattice here. Let's just focus on this side to start with. And then if we can imagine that we sort of cause that to crack along that line there, and we basically try and force this part of the crystal down, or this part up, so this part down with respect to the other part, what we can see is we're going to lead to this sort of situation here. And what you can see here is now, as that moves down, suddenly the positive charges are next to each other, the negative charges are next to each other, more positive charges next to each other. And what that is going to cause to happen is that basically now we are going to get repulsion between those like charges. So all those like charges are going to try and repel away from each other, so push away. So the result will be, if you like, this plate here gets moved out this way with respect to this part here. So because of the nature of that lattice of opposite charges, if we get a small deformation, we suddenly end up with a situation where the like charges are next to each other, like charges will repel each other, and that is what will cause that, if you like, that shattering or that brittleness that you would see in an ionic compound. That's it for ionic bonding. Thank you.